All right, something just fell right there. Here's your homework video. So if you need support from me, here it is for the remainder and factor theorems. So let's do it together. Can you use synthetic substitution here? So don't change the sign. Positive 2, 410, negative 15, negative 21. Just do the synthetic division. Add and multiply. Take a second, like me, write that. That's what, 21, 42, 21, I think. Double check, yes. So what did I just find? That f at 2 equals 21. Done. So we're a different way to do substitution. Let's try it again. Negative 1, 2, negative 4, 5, negative 9, and 0, because we're missing a constant at the end. So add and multiply. And so what did we just find? F at negative 1 is equal to 20. Again, number 3. Can you do a synthetic substitution? Keep the sign the same. 2, 6, negative 2, negative 1, negative 14. Nothing missing. Add and multiply. Double check. Beautiful. We just found f at negative 3 equals 29 by doing a different way to do substitution. Number 4. Oh, we're missing a term. 0. Missing x squared. Negative 24, negative 48. So don't forget a missing power if you see it. That's 3, 12, 3, 12, 48. 24, that 80 and 16, 96. That's 48, right? Half. Done. So what do we just find? F at 4 equals 48. Done. Using synthetic substitution instead of your old-fashioned substitution. How do you know if a factor is this? How do you know? It's when you do synthetic substitution and the remainder is 0. So are any of these factors? So let's go one at a time. So negative 6, 3, 13, negative 32, negative 12. So no, I can already tell that's a no. Make sure. See, once the numbers get so large, I know it's not going to equal 0. Then I don't bother with it. What did I do wrong here? The answer key says I'm wrong. So let's see. Oh, this is negative 5. This is positive 30. This is negative 2, positive 12. Silly me, that totally is a remainder of 0. This one works. Don't make a silly mistake like I do with signs. Take your time. Here we go, one more. How about this one? Positive 2. So positive 2, we have 3, 13, negative 32, and negative 12. Let's see if I don't make a silly mistake here. That one looks like it works because it gives you a remainder of 0. One more, negative 4. Does that one work? Maybe they all work. So does negative 4 give you a remainder of 0? Nope. That's going to be positive 120, 100 and what? 44, 100. I get 120 and 24, 144, but obviously not I don't even care what the remainder is. It's not 0. This one does not work. So you see the two that do work and the one that doesn't work. All right, how do you know if this is a factor? Synthetic substitution. So we're going to go positive 1, 4, 52, 87, negative 13 and negative 22. 13, 143. This certainly doesn't feel like it's going to work, and it doesn't. So once I realize it's not going to give me 0, I don't do it. It's done. Let's do the next one. So negative 11. Set it up. Definitely gives me a remainder of 0. That one works. Now, I'm just going to use the remainder, so I'm not going to go back here. These numbers are smaller. I can use those. So once you know one works, you can use the simplified version. So -2, I'm just going to use it and not even write it all over again. So -2 and see if it works. Totally gives me a remainder of 0, so that the bottom two work, but the top one didn't. All right, next page, last page for your homework. Use the factor theorem so that we can factor it completely. That's our goal. So we're given one of the factors. We're going to take the 0 of that, +4, and see what's left. So there I go. Let me have something to write on that's not digging in here. So 1, 10, and 24. So 1 degree less, that's x squared plus 10x plus 24. This is a simple trinomial because it's 1x squared. So two numbers that multiply to 24 and add to 10. So that's 4 and 6. So now let's put it all together. The factor we began with, x subtract 4, and then the two that we found, x plus 4 and x plus 6. And remember, you can always press pause when this goes too fast. Number 8. You're given x plus 6. The 0 is -6, so we start there. 2, 13, -15, -126. So that gives me a remainder of 0. I have 2x squared plus 1x minus 21. Not simple because it's not 1x squared. So I'm going to do a little x. I'm going to go 2 times -21 is -41, or 42 I mean, and then +1. So those two numbers that go -42 and 1 are 7 and -6. They multiply to -42 and they add to 1. So I'm going to have 2x squared plus 7x minus 6x minus 21. So I set this up to do factoring by grouping. So the first two terms, you factor out an x, and you're left with 2x plus 7. Factor out a -3, and you have 2x plus 7. Put it together. So you have one common factor, 2x plus 7, and what's left over? X subtract 3. Put it all together now. So the one you started with, you were given x plus 6, and then the two that you found, 2x plus 7 and x minus 3. Done. Number 9. You're given x subtract 3 as a factor. So we're going to take what we're given. If there's any missing powers here, be careful. So 0 is a missing power. Here we go, 16, 48, that's 0, that's 0. So this is what's left. 1 degree down, so that is 16x cubed minus 9x. No x squared, no constant. Take out a common factor of x, and you have 16x minus 9. That's it. Just double check here. I have a second computer here for fun. Make sure I did it right with the answer key. Oh, and then it tells me to get the zeros from this. All right. So I'm going to go back and make sure we did the zeros. I'll do that at the end. So for number 9, this should be x squared. That's where I made a mistake. So what's left over here is a difference of squares. So the square root of 16, x squared is 4x. The square root of 9 is 3. So 4x plus 3, 4x minus 3. So let's put this all together. And now, oh, and the one we started with, which is x minus 3. So here's what I found, and don't forget what you were given. Now, what are the zeros here? So I'm just going to label it zeros. X by itself, the 0 is 0. Here, subtract 3 and divide by 4, add 3, divide by 4, and just add 3. Let's go back up to make sure I didn't make a mistake up here. So what are the zeros here? Make sure I do that one correct. That's positive 4, negative 4, and negative 6. So each factor, the inverse, are the zeros. So once it's factored, it should be easy. Here again, what's the inverse? Negative. So subtract 6. Here, subtract 7, divide by 2, add 3. So you have your zeros once it's factored. All right, number 10. This one's going to be a long one. I feel it. Negative 4, 1, 4, negative 26, negative 104, 25, and 100. Here we have 80 and 24. I think that's 104. All right, so we definitely have a remainder of 0. Next, 1 degree less. So that's 1x to the 4th, no x cubes, minus 26x squared, no x's, plus 25. Now, that's in the form of a quadratic. It isn't a quadratic, but it's in the form. So it's simple too, so I don't even need this. What are the two numbers that multiply to 25? So instead of x, it becomes x squared. And then what are the two numbers that multiply to 25 and add to negative 26? So negative 1 and negative 25 fit. They multiply to 25, they add to negative 26. Then what's left is called the difference of squares. So the square root. So square root of x and 1, x plus 1, x minus 1, x plus 5, x minus 5. So those are the ones we found. So now let's put it all together. So the one that I was given was x plus 4. What I found was x plus 1, x subtract 1, x plus 5, x subtract 5. So those are the ones I found. So what are the zeros then? So the inverse, so instead of adding 4, here we have positive and negative 1. Here we have positive and negative 5. And you have the zeros that go with it. All right, number 11. The value of a rare baseball card. So the value of a rare baseball card issued in 1989 is represented by this function where x represents the number of years since the baseball card was issued. Use the remainder theorem to find the value of 1999. So if this is true, and this is since 1980, x represents the number of years since, 89 to 99, that number would be 10. So I'm going to use 10. No missing terms there. So I just use the coefficients. 10 means you move the decimal. I'm going to treat this like money, like $2 take away a quarter. That's $1.75. Multiplied by 10, you move the decimal, it's 17.5. This is 20.5. Okay, again, multiply times 10, move the decimal, that's 205. So I get 209 as the price. Double check. Perfect. So in 1999, the value of the baseball card was $209. All right, Mr. G Math, over and out. Till next time.